Weak acids and weak bases have much lower ionization constants. Here's a list for some typical weak acids and bases. Usually, we call it weak acids or bases if the ionization constant are less than 1 but greater than 10 to minus 14. If the ionization constant is less than 10 to minus 15 or 16, the acid or base is too weak to affect the pH of the solution. We don't need to consider its ionization, and the solution of these acids and bases are neutral. For example, see the table of acid. The last row, the second step ionization of hydrogen sulfide is 10 to minus 19, which means the ionization at this step is completely neglectable. Consider the ionization of a weak acid at equilibrium. We can get the Ka expression with a tabular approach, assuming X moles per liter acid ionizes in the process. It's a weak acid. The concentration of the ionized acid is low. So X is less than C0, can be neglected. Then we have Ka equals X squared over C0. This formula can be transformed to X equals square root of Ka times C0. One more step. We get fractions of ionized acid by dividing X with C0. We have the relation between alpha and Ka over C0. From this formula, we may conclude that at constant Ka, the lower the concentration, the higher the ionization degree. Although this is a conclusion from an approximation, you can see the approximation from the graph on the right. The dashed line shows the ionization go to completion, while the exact results shown by the solid line tell us that there are arrows when the initial concentration is very low. See the green area for the arrows, but such an approximation is acceptable for most applications.
Question: calculate the proton concentration of 0.012 moles per liter formic acid aqueous solution. Let me write down the chemical equation first. Formic acid to proton and anion HCOO-. Then we use a tabular approach to show the concentration change in the process, assuming X moles per liter are converted. Then at equilibrium, the concentration of formic acid is 0.012 minus X. The proton is X. The anion is X. We have the equilibrium constant Ka equals X squared over 0.012 minus X. Here, you might use approximation to cancel the X in the denominator of, and the calculated X is 0.00147. But if you check the ratio of X value to the initial concentration, 0.012, the result is 0.05, which means you cannot use the approximation. Otherwise, the error in calculation is too large. We have to use the quadratic formula to calculate. We had the Ka expression, then we have the X expression as shown here, with values are plugged into. The final answer is 0.00139.
Some anions from salts can be either protonated or deprotonated. See the example. Dihydrogen phosphate ion. Can we predict the solution of the ion is acidic or not? Before we can predict, we need to know the relationship of Ka and Kb in a conjugate acid-base pair. Here, Ha and A- compose a conjugate acid-base pair. One proton difference in the chemical formula. We can write down Kb expression of protonation of A- ion as shown on the right. When we multiply Ka by Kb, we find the product of Ka and Kb is Kw. Then the ion product of water. Now we get the relation of Ka and Kb. For the question about the dihydrogen phosphate solution, we can calculate Kb1 for the protonation of dihydrogen phosphate ion. Kb1 is 1.4 times 10 to minus 10. Then we can compare Kb1 with the Ka2 of the deprotonation of dihydrogen phosphate ion. Clearly, Ka2 is larger than Kb1. The ion tends to be deprotonated, so the solution is acidic.